So just to recap for people from last lesson, if you were away, question 8, we went through, you can hopefully read most of the stuff here, but if you're looking and you go, what's happened to the fraction? I left it blank. So there is actually a fraction here. You sort of have to fill that out. Okay, so still there. Are we happy that we finished 8 or not? If you didn't, hopefully you'll have time, I don't know, maybe in our double where I won't be jabber-jawsing out the front too much. I can come around and circle. So, question 8, the example question 16 I asked you to look at very quickly, and then you want to try and apply that with question 9. How did we go?
9A1 is good. Oh, no, they were good.
So, 9A1 is very similar to the example. So who didn't do 9A? Whoopsies. Well, you were away, you understand that. So with 9A, for those who have done 9A, and you don't want to wait for us to do it unless you want to listen, you are more than welcome to go and have a start at 11, because it's very similar while you wait for us, and those people can do that for homework tonight. So let's have a look. While I'm just setting up, you are making sure you're looking at that example. They just had this question by itself and going, use complex numbers methods to deduce this, and you hadn't actually looked at that example, I would understand why you might be just a bit swimming at sea. So if we go back and look at the example here, you can see that in order to find expressions for cos 2 theta and sin 2 theta, you actually started with cis 2 theta, right? So if we now want to find expressions for cos theta and sin theta, what do you think we're going to start with? Cis 3 theta, okay? So we will start with cis 3 theta, and we're working backwards with de Moivre's theorem and de Moivre, right? And we're saying that that's to the power of 3. Agreed? We are hitting that point where we go, when we're proving things, do we want to keep it as, sorry, my phone was on, cis theta all the time and just use its properties, or do we want to convert it to cos theta plus I sin theta? Now, what would be the answer to that? Keep it as cis or convert? Clearly convert, because if we're looking at what we're trying to prove, we've got all these causes and sines around the place. So in order to get that, we have to convert it to, right? And we've just figured out who's a sucker and who's a cruncher. All right, so people listening to the video will go, what is she talking about? We've got chopper chops. So we've got that. We get a little bit excited, flashbacks to lovely times when we have to use what to expand that bracket? Pascal! My fave. All right, so that becomes cos cubed theta plus, who would like to take over? 1, 3, 3. Good. So 3. First one is got the power of 2. Then I sin theta plus 3. Cos now has just power of 1. And this is where you need to be careful, because your second term has got the power of 2. So this will be I squared sin squared theta plus the last one, I cubed sin 3 theta. Equaling, and so technically cis 3 theta is, in fact, cos 3 theta plus I sin 3 theta, right? And again, if you go back, I'm expecting that you had looked at that example, and this was another technique where we do the equating, the real and the imaginary. We're going to do that several times in this topic, okay? So if we look over here, what part on the left-hand side is our real part? Cos 3 theta. So if I'm going, let's have a look at the real. And what on our right-hand side is our real part. We still have to do a little bit of work here because, yes, we've got the cos cubed, but is there anything else that I can actually make or simplify? Yeah, Josh, yep. Right, this bit here, I squared, we can replace with minus 1. I cubed, it's not going to make it go totally, but what can we rewrite I cubed as? Negative I, that's right, because it's I squared times I, so minus I. So we've got 3 and you know, if you really wanted to, you could put the I out the front for that. I don't bother. So I squared is minus 1, so minus 3. And this would be minus I sine cubed. You good with that? I'll stop for a minute. Left-hand side of the real is cos 3 theta. Boy, there's a lot of 3's and thetas that I have to say this morning. And then on the right-hand side, what's the real part there? As we said, we've got this part is real and this part is real. So we now end up with this being cos cubed theta plus, minus, why does this come up again? Go away, go away. Minus 3 cos theta sine squared theta. Now, we're very impressed with ourselves, expanding all of this, grouping it all together, and we go, yeah, are we done? Reread the question, and we're going, oh, that's not what we've ended up with, is it? What's the difference between theirs and ours? Oh, it's right up here. Didn't have to go back to the thing. What have we got that they haven't got? Yeah, not just a sine, but a sine squared. So is there any possible way that we could replace sine squared?
Yeah, you do using the formula.
Using the formula, yeah.
You can get 1 minus cosine squared.
Right, so remember that we have sine squared, our little mate. What is with my writing today? Sine squared plus cos squared. Keep up with me, board. So I can rewrite sine squared as 1 minus cos squared, agreed?
Yeah.
So we've now got cos cube theta minus cos. I hope I'm starting to see a few smiles out there. Why would we be a little bit smiley, a little bit rejoicing? Yeah, Josh? Yeah. Correct. He said if you expand that out, so 3 cos theta times 1 is 3 cos theta. Negative 3 cos times negative cos squared gives you a positive 3 cos squared theta. And lo and behold, cubed. So I've got a cos cubed plus 3 cos cubed, so that gives me 4 cos cubed minus 3 cos theta, which is, huzzah, what we were after. We good with that? We're going to do exactly the same with the imaginary. So on the left-hand side, our imaginary is sine 3 theta. Now, I'm going to ignore the i's because that's the bit that's telling me it's imaginary, right? It's saying put that on the imaginary part, and on my right-hand side, my imaginary part is? Correct. So we end up with, pop that up a little bit for me. Whoops. So we end up with sine 3 theta on the left-hand side, and that's one of the things we wanted an expression for. On the right-hand side, we're not including the I there, so I've got 3 cos squared theta sine theta minus, and again, don't include the I. And once again, you have to now try and see if you can get it to look like this. So I will say no more and you just do. At least start with. Great. So we've got tan 3 theta equals sine. So even if you hadn't finished that earlier bit, we can still do this part, or do as much as you possibly can, because hence is saying use what you've just done above. Now, clearly, what can we see above? We've got sine 3 theta, we've got cos 3 theta. So let's slap it in. 3 sine theta minus 4 sine cubed all over. Anything we see that we might want to be able to do here? Excellent, right? We can see there's a common factor of sine on the top and cos, and so well, that's a bonus because we would then have sine over cos is, well, at least we've got one of them, so that's great. So we're going to pull out the sine on the top and we're going to pull out cos on the bottom. So you can do that. Stay a step ahead of me, please. Okay, we're reasonably happy here, and we can now replace sine over cos with tan. So that's not too bad. I feel like I need to write smaller or make a bit of a gap. Now, I don't know if it shocks you or whatever, but I sort of do these for homework as well. So I had a look at this, and because of the stuff we were just doing before, I was like, oh, what can I do? What can I do? Just blindly going, well, I can replace sine squared with 1 minus cos squared. But I just got myself into a bit of a pickle, and it didn't really go very well. I'm coming, Josh. And so we're then thinking, well, if I did that, that's no good. Remember, what we're trying to do is end up with tan theta. Part of me is going, well, I could actually divide by cos squared, couldn't I? Because what's sine squared divided by cos squared? Tan squared. Now that's in terms of tan. Problem is, and good here too, what I do the top, I have to do the bottom. So I divide this by cos squared, yep, I get a tan squared. I divide cos squared by cos squared, it cancels out. That's pretty good. But I'm then left with 3 over cos squared and another 3 over cos squared, and I'm not allowed to cancel them because there's that minus in the middle, right? So it's just going to make that awkward. So I trialed these things, right? And that's what, if we had a heap of time, I would let you or make you do. Can't do it. Or we haven't got that time. So then we went to plan C. So I had plan A, I had plan B. Some of you might have gone straight to my plan C. But for me, it was the 3s. I had to try and replace them in terms of cos and sine. So the thing that we just used before, this one here, I'm actually going to use that and say that it's 3 times sine squared and cos squared. Yes? Again, wouldn't have been my first go-to, as I just explained to you, but it's because the other ones failed, I went, oh, well, now I'm going to try this. So I've got, would you agree this is now 3 sine squared plus 3 cos squared minus 4 sine squared. And down the bottom, I'm going to do the same thing. That's going to be 4 cos squared minus 3 sine squared minus 3 cos squared. Sam, I love that. I just went, oh. I heard you go, oh. It's the delight. I have to leave a gap because it's getting very messy there. Tidying up, that's going to be 3 cos squared theta minus what's that? bit disconcerting when I'm right at the front of the board here doing my thing. So is that okay, people? And going back to the question, write it in terms of tan only. So that means no cos, no sine, just tan. And that was what we were talking about before is I've got the sine squared here. I know that sine over cosine is tan. So if I divide this by cos squared, what do I get? Tan squared. But the bonus now is I have to divide the whole thing by cos squared, right? What's cos squared divided by cos squared?
1.
Right, cancel. So I just get 3 times 1, which is 3. That's not a sine, it's not a cosine. And then here, cos squared divided by cos squared again is 1. Sine squared divided by cos squared. Now, I would not normally think to do that, but because it was telling me up here, I want it in terms of tan. As I'm going through this question, in my head, or even on paper, right, I have got tan theta equals sine over cosine, and I'm trying to make sure that I use that wherever I possibly can. So what we will now do is I will divide the top by cos squared theta, and I will also, oh, I shouldn't have put that over. Never mind, get rid of that. And I will also divide the bottom by cos squared theta, and what I do to the top, I'm doing to the bottom. So technically, I'm only dividing by 1. Legal maneuver. Okay, so what I end up with now is I've got my tan theta. This divided by cos squared, that's 3. Sine squared divided by cos squared is tan squared. Cos squared divided by cos squared is 1. 3 sine squared divided by, I get minus 3. And there I have it. I have simplified tan 3 theta in terms of tan only. Now, if you really wanted to, you could times through by the tan there. I'm not going to. I'm keeping it out. Because you think, oh my God, I've done all of that hard work and now it's got hence solve this. And you go, seriously? Where is this just lobbed from? So again, you're looking at the hence factor and you've got to look upstairs and see, is there anything that relates to what I've got? Now, Josh has got his hand up and he can see something. Give them a moment, Josh, and then you tell them. Or I saw Sam nodding. I mean, I can only see 2 things where there's a 4. Where do we see 4 something cubed minus 3 something? Thank you. Up here? Okay. So, how can we use that though? That one and that one are linked. So, if I replaced x with cos, can we then say that this whole thing then would be the same as cos 3 theta equals minus 1 on root 2? And now we solve that. So it didn't say to do it algebraically, although if we wanted to, going back to the good old days, can you remind me how we solve this? What are you up to? Are you doing trig in methods at the moment? Oh, well, let's get pumped for methods. I'll do the brighter green so you can see it. Unit circle, so I do this where I look working angle. Okay, so cos of what equals 1 on root 2, technically root 2 on 2. That's 45 degrees or pi on 4. And then we look at in which quadrant is cos going to be negative. Now remember, cos is your x-axis. So where is your x-axis negative? Right, lefties. Lefties, lefties. Correct? So we've got a whole pi. What's a whole pi take? 1/4. 3/4. What's a whole pi? 5 pi on 4. I've got people not paying attention. Does that mean you know what you're doing, or you've now put your head down and going, I'm just going to tune out? Do you remember this? And so therefore, 3 theta will equal 3 pi on 4. 5 pi on 4 plus 2. It should have been k lots of 2 pi, but I don't know why. I always write 2k pi. Anyway, we don't want that. We want theta. So we divide by 3. So that's going to be 3 pi on 12. I know I can cancel that, but I tend to do that right at the end. Do I have to divide?
Yes.
Why? They said yes. Why? And they're correct. Yeah, but if I had like theta take pi on 2 equals blah, 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 k2 pi, and I'd add pi on 2, add pi. Do I add pi on 2 to that? I don't. Why? Yeah?
When you look at it on the graph, 3 theta takes the period.
Right, it's the number in front of your b value, right? Sine b theta, cos b, that's the one that affects your period. This one, what does that do? Horizontal translation. Very good. So it doesn't affect the period, but this one definitely does. So we're now going to add 2 k lots of, there we go. Did it nicely this time, and you can do that for, did it say? I'd probably, if it doesn't say, I'd go for 0 to 2 pi, but we've got all of our options here anyway. So I would just make sure I finish off and say that would be pi on 4, 5 pi on 12, plus k lots of 2 pi on 3. We talked about this a little bit earlier. Do you remember how to use your solve n to get that within the period? You remember how to put your period in? The comma, that's right. I know some of you said yes, we remember, but some nodded and looked blankly at me. So anyway, so to do solve n, we go option, calc. You all know the solve n, and we would have typed in cos 3 theta equals, what do we have? Was it negative? Oh, thanks. Negative 1 over root 2. And go up there, pop your comma in, pop your x value in, and then you do between the period that you want. So I'd be going 0 and 2 of the pi variety, making sure that your calculator is indeed in radians. And that's something that you're going to have to keep checking, especially when we do vectors, because we might be flicking between degrees and radians. So always double check. And there we go. So those were our first 2 solutions, and we're getting all of them here, but we're covered in our statement here. We're covered by saying plus k lots of 2 pi.
Would you need to specify that k is an integer?
I should have specified k as an integer, yes. Thanks, Sammy. And I just double check. It did not say between 0 and 2 pi. It didn't. So, yeah, I'd leave it like this. All good? You want to sub? Yeah. That's what we do, right? So we've got z equals cis theta. So we're happy with this, that this would be cis theta to the n. Now I'm thinking ahead, and I'm going, it's quite happy I can go 1 over cis theta to the n, but would you be okay if I also did this? All I've done is I've moved this up. Remember, this is our unit on de Moivre's theorem where we're dealing with the powers. So just wanted to make my life easier. If I had done 1 over cis n, well, putting it up, you'd put it to the minus power, much of a muchness. Okay, we've got cis theta. I could, well, let's just do it all in one line, I guess, plus cis theta to the minus n. So now using de Moivre's theorem, we've got this. And if we're after, you know, being impressive, dm, we've used it there. Now what? Right. Remember we said whenever we've got cis, are we leaving it as cis and using the properties of cis? In this case, we look at what we're trying to do. It's got a cos theta in there, so it's basically telling us sub it in, replace with cos theta plus I sine theta. Remember, explaining what you're doing. So they're now going to cancel, and lo and behold, we get what our right-hand side was meant to be. Okay, because I sine theta minus I sine n theta cancel out. I've got cos n theta plus another cos n theta. Last time I checked, that's 2 cos n theta. We're good. All right. All right, hence, explain. That one's not a tricky one. Jules? Yep, n equals 1. Good. So write a little statement, n equals 1. All good. Please. You do 3. Everyone was happy with part 3. Yes? You all did that nicely. And now we're sort of going, yeah, okay, hence show that cos cubed is blah, 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 blah. Hence. Now, what do we notice here? We've got this, and we've got this. And we've got this. So, for part 4, z plus 1 over z, isn't that in fact 2 cos theta? So that's going to be 2 cos theta cubed. Agreed? Equals z cubed plus 1 over z. Using that, what can I replace that with? N would be 3. Agreed? So that would now be 2 cos 3 theta plus 3 times, now what's z plus 1 over? Times 2 cos theta. Fiddle and get cos cubed by itself. Now the reason that I wanted to do at least that bit was because maybe the next bit is a little bit ugly. I want to get to that. But part B, very similar to part A. It's got a nice little hint for you to do that. So try it. Leave a bit of a gap if you can't do it. The very annoying thing is if you actually put that into your calculator, it gives you that. They're so good these days. Back in the old day, they wouldn't. I reckon I want to go and check our slightly older version as well to see if they do it. But our calculator's now awesome. So please, 12, go back, finish off anything you haven't done. Please start review set A.